In this video, we're going to look at energy conversions during cellular respiration. So we're going to start by writing the cellular respiration equation. So we start with glucose, and we add on 6 oxygens to produce 6 carbon dioxides and 6 water molecules. So it's kind of like a combustion reaction. Now, cellular respiration is an exothermic reaction, meaning that energy is released as it's converted from potential to kinetic. And so in this case, energy is going to be a product in our reaction. So we're going to look now at the schematic for the cellular respiration reaction. So once again, this is an exothermic reaction, which means that energy is going to be released. So in this reaction, we have our reactants, glucose and oxygen. These combine to form carbon dioxide and water. And when these combine, we also get a net release of energy. This release of energy has to do with the stored potential energy in the chemical bonds of glucose. So in glucose, there's a lot of energy stored in the chemical bonds. When these bonds are broken, so if you see we have carbon-carbon bonds and lots of carbon-oxygen bonds and oxygen-hydrogen bonds, these bonds are broken and rearranged to form these carbon-oxygen bonds and these oxygen-hydrogen bonds. So when we break these bonds in glucose and oxygen, and we form carbon dioxide and water, the bonds in carbon dioxide and water have less potential energy than the bonds in glucose and oxygen. And so there's a net loss of energy, and we make up for that by releasing or by accounting for the kinetic energy that's released. So we're going to look quickly at just the schematic of this reaction over time. So in any reaction, our total energy is going to be conserved. And so we're going to start with our potential energy. And we start with our reactants. Now our reactants have quite high potential energy. So glucose plus oxygen. This potential energy, as the reaction proceeds, will decrease until we form our products of carbon dioxide and water. Now this loss of potential energy goes into the kinetic energy of our surroundings. So our surroundings start out with some amount of kinetic energy, and as the reaction proceeds, that amount of kinetic energy increases. And so we have a net gain of kinetic energy within our surroundings. So in this scenario, our total energy remains the same, but we're converting from one form within our system. So we're converting from potential in our system to kinetic in our surroundings.